Wikipedia lists several renders for Maya: RenderMan, 3D Light, Vray, Holomatrix, Furry Ball, and Octane. There is also Solid Angle for Arnold. This other website lists Optics, Arian, Furry Ball, Lightworks, Octane, as well as Vray. There is also OX1 for iRay. This is my network. It has 12 nodes and 1 workstation. From this Vray reseller, I had to buy 1 copy of Vray, which was nearly $1,000, as well as register my network nodes, which cost nearly $2,000 for 5 extra nodes, and a total of $3,000. This is why I called it rendering for adults, because you have to spend nearly $3,000 to set up a simple network. That is, in addition to the cost of Maya. Maya comes with another render, Ray for Maya. The cost of Maya is $123 a month, or a one-time cost of $3,600. Today we're talking about distributed rendering over a network. Ray for Maya and Vray are the only renderers that allow you to distribute a render over the network, while Ray is limited to 4 nodes because of its registration and licensing. In another lesson on this YouTube page, I show how to set up and use Ray Satellite for Maya. Today we're going to be using this scene with a rock on a Windows 8 computer with 2 Opteron 6300s and 256 GB of RAM. It also has an NVIDIA Quadro K5000 and a Tesla K20, which have a total of 5,000 CUDA cores and about 12 GB of video power. This rock is from the RockGen script on Creative Crash, and it is textured using textures from myang.com. We'll start using Ray. With the default settings, it takes about 5 seconds to render our simple rock. The rock has 3 textures: a diffuse, a bump map, and a specular. Next, I'm going to set up the network render, which I go over more thoroughly in the tutorial. First, we go to our rendering menu, the rendering drop-down tab, then we go to the batch render, the options box, and turn on render on the network machines. Next, I have to debug my network. I'm going to start by turning on 4 nodes and making sure that they are connected to the workstation and detected in the network tab. Once the network is debugged, I'll render again. First, turning off the local machine. If we look in the output window, somewhere there is a line of text that says that Maya has connected to the network machines. But eventually I give up looking for it and go on to the next section. There is no significant advantage in this case using this small scene, as you can see that it also takes 5 seconds to render the rock on the network, the same as it does on the local workstation. Later on, we'll go into large renders, which shows the significant increase in efficiency by using a network. I'm going to turn on another 2 nodes in the network to display how Vray works. First, we want to switch over our renderer to Vray. Then we're assigning a Vray material to our rock. And watching myself get confused. Here is our rock rendered with Vray. It takes 3.8 seconds to render on the local machine. By going over to Settings and Use Distributed Rendering, and then going down to the Settings tab, you can see that we can use an unlimited amount of render nodes, which is one of the benefits of using Vray over Mental Ray. Next, we're turning off the local machine and trying to render our rock again. As you notice, there is nothing happening, which is usually a good sign that something is not working. If we open up our output window, we see the warnings that it could not connect to the network. The reason is because the network nodes are not registered as a slave node for Vray. Here I'm launching the slave node for Vray on each of the workstations. The first thing you notice is that there's no textures on our rock. If we go back to the render settings and we click on Transfer Missing Assets, it will transfer the file textures to each of the network nodes. If we render again, you see that we do in fact have all of our textures, and it takes about 3.3 seconds. So there is a benefit even using this small scene. Usually, when you load the Vray render node onto a workstation or a slave node, it is registered as a service. As you can see here, Vray Maya Spawner for 2013. I have it turned off. If we right click and go to Open Services, and then find the Vray node under Services, right click again and go to Properties, we can see in the startup type that we can change it from manual to automatic, or we can turn it off altogether. For some reason, my network doesn't like running services between Windows 2012 Server R2 and Windows 8, so I'm using it manually. This quick launch icon can be found under the Start menu. I just have it pinned to my desktop. Next, we're going to talk about interactive rendering. If we open up the Vray RT tab on the render settings, we have the choice between CPU, OpenCL, and CUDA. I'm going to set CUDA because it is by far the fastest. When I first start the render RT engine, you can see that something is clearly wrong. If we go back to our render settings, we'll notice that we forgot to turn off distributed rendering, so it's still rendering on the network. We'll go back to using the local machine because the Supermicro microcloud does not have CUDA. If we close down the render RT and start it back up again, it is now using the NVIDIA Quadro and Tesla on the workstation to render. You'll notice that it updates instantaneously. If we scroll down in the Vray material to the bump map section, and we start adjusting the bump map, you'll see that the Vray interactive rendering shows us different values for the bump map immediately. This is helpful when going through our workflow to develop our models. Next, we're going to change to another material so I can show this other function. We have a procedural checker texture applied to our second material. If we change the tiling from 4 to 8, you'll see that it also updates immediately using the CUDA render. Now we're going to switch back to Mental Ray and use Mental Ray's interactive renderer. Mental Ray uses IPR. If we open up IPR and then open up a selection mask on our window, we can see that it starts rendering immediately. Obviously, it takes a lot longer because Ray does not use either OpenGL or CUDA, so it's using the CPU. If we do the exact same test, and we go to the bump mapping, theoretically it should update interactively, but as you can see, there is no change at all using Ray. The buckets are rendering the picture, but they are not taking into account the changes in the bump depth. Sometimes, by closing IPR and opening it up again, we can see the changes in the bump depth. However, this counteracts the purpose in using an interactive render if you have to shut it down and open it up again every time. Perhaps this is a bad example, as you'll notice that the bump depth on our bump map does not seem to be affected at all. Perhaps there is a subtle change, but having to close down the window and reopen it, we can't tell. Again, we'll sign a different material for Ray, also with the checkered procedural texture. Using the IPR to check to see if Ray updates the procedural texture. In this case, Ray handles the Maya procedural texture rather well, but it's been my experience that updating a tiled procedural texture in fact does not work when working with a scene. IPR gets confused when you have multiple texture nodes or multiple objects in the same scene, and refuses to update a tiled texture. Here, I'm showcasing the three different types of the Vray RT engine. I'm using a basic broadleaf tree from Onyx, which has about 600,000 polygons. First, we'll use the CPU. Pay no attention to my mouse, as you'll see it's offset about 2 inches. When using the CPU, there is a small amount of lag loading the Vray RT engine. If we open up the Task Manager, we can see an instant spike in CPU usage. And although there is a little bit of lag, it does in fact load the picture fairly quickly, about 2 seconds. When we turn the scene in the interactive render, it refreshes also in about 2 seconds, although there is a slight lag using the CPU. We'll reset our scene and switch the engine type over to OpenGL. Given the Opteron has 32 threads and uses an AMD system. In this case, there is a significant lag when opening up the scene. There doesn't seem to be a large strain on the CPU or the RAM, but it does take nearly 4 seconds to do the interactive render on the tree. When we go to pan our scene, there is a significant lag of nearly 2 seconds again, from the time that we direct the camera to pan until it actually pans and starts rendering, it takes about 4 seconds again to refresh the scene. There is also a significant increase in RAM. The OpenCL uses 2 GB of RAM more than the other functions. Also, when turning it off, there is again a 2-second lag when hitting the button before it reacts. Resetting our scene again, we're showing the CUDA. As I stated, the combined video cards have about 12 GB of power and 5,000 CUDA cores. We notice that opening up the Vray RT is almost instantaneous. There is no significant strain on the CPU or the RAM because the calculation is done completely on the video card. Again, it takes about 1 or 2 seconds for it to render the scene. When panning the scene, you can see again that it is almost instantaneous and there is no lag at all. Overall, with this setup, CUDA is the best choice for interactive rendering on Vray. Here's the scene that I'm showcasing render times. It has 300 million polygon leaves, each using ray tracing and global illumination. I'm doing a real-time render here because I was enchanted at how fast it worked on the network render, like a herd of caterpillars chewing through 300 million polygon leaves on the trees. When you see the comparisons after this short video, you'll understand why. Given again, you have to take into consideration that each one of these leaves has a translucence texture, a transparency texture, a bump map, as well as a diffuse channel, a specular channel, and the ray traced light passing through it. Each one of these buckets is calculating the sum 300 million ray traced shadows that are used in this scene. This scene is also being rendered at true 4K, which is 3,860 pixels by 2,140 pixels. If you'll notice on the network, it's transferring roughly at 2 megabytes per second, back and forth between the workstation and the network nodes. In this case, I could probably raise the size of my buckets to take full advantage of the gigabyte switch. After the initial pass, I have the brute force engine set up to progressive, so it doesn't use buckets. If you'll notice down in the lower left corner, it is calculating the global illumination rays, which takes a few additional seconds. In this instance, I'm using irradiance mapping with no secondary bounce for my global illumination formula. Once the rendering is finished, if you'll notice, Windows is now authoring the file, giving it a file name, attaching the render data, and assigning it to a temporary folder, which takes about an additional 10 seconds. Initially, when I rendered this same scene in Mental Ray, it took 4 hours to render on my laptop, and it also took 1 hour and 30 minutes to render on the network with the 4 satellite nodes. Here, Vray has rendered this same scene in 2 minutes and 45 seconds. Initially, it took 8 hours and 46 minutes on the laptop with Vray, 1 hour and 3 minutes on the network with Vray, and 2 minutes and 46 seconds with a single irradiance mapping, and 1 minute and 30 seconds with brute force. Personally, I can't tell the difference between the brute force and the irradiance mapping from 8 hours to 1 minute and 30 seconds. The pros of Vray are the unlimited network nodes. It supports a GPU and CUDA, it has faster renders, and it adjusts textures and bump in real time. You can also emit light from objects, which Mental Ray cannot. The cons are the cost. It's not native to Maya, it doesn't have as many utilities, it doesn't share a network drive, and it takes an education to run. The pros of Mental Ray are it's native to Maya, there's many extras, it can network a drive, there's many references online, and many lighting profiles. The cons are that it's limited to 4 network nodes, it doesn't use GPU or CUDA, it has slower renders, it doesn't real-time textures or bumps, and also takes an education to run.